All right, this is section 7-2, Properties of Exponential Functions. All right, so this is 7-2, Properties of Exponential Functions again. And please ignore the background chatter from Kendra as we go. Okay, so the objective for this section was to explore the properties of functions, exponential functions in this form, y equals ax plus b. Also, we're going to talk about how to graph exponential functions that have a base e, which is a special kind of irrational number similar to pi. Okay? So here, our central understanding, the factor a right here can stretch or compress the graph of y equals b to the x power. That is the parent function. So this number right here, depending on what it is, can stretch or compress the function. Okay? Here's a graph of two functions. We see that the blue one, or sorry, the one in red and the one in blue just have one difference, the 3 out in the front. So the 3 out in the front is going to actually stretch this function out. They start almost in the same place, but the blue one is a little more stretched out. Okay? So now we'll see what each one of these different things do. So we start with the parent function. If the absolute value of a is bigger than 1, that stretches the function. If the absolute value of a, which is right here, if the absolute value of a is between 0 and 1, it compresses the function. And if a is less than 0, that means if there is a negative in the front, is the reflection about the x-axis. There's one more kind of reflection, which is if the exponent is negative, that's a reflection about the y-axis. I thought that was just the case. Right? So if the negative is out front, that's a reflection in the x. If the negative is in the exponent, that's a reflection about the y. So an x reflection would be a graph looks like that, suddenly looks like that. A reflection about the y turns exponential growth into exponential decay if there's a negative in the top. Okay, so next, translation. So translation is when we have something else in the exponent. It is a negative. It goes to the right. If it is a positive, it translates to the left. This number, the k, is a vertical translation. A positive translates it up, a negative translates it down. And here's an example of a function that has a little bit of everything. Bless you. Next, let's graph these two functions. We'll do the first one in red, we'll do the second one in blue, and then we'll compare the two. So first, let's choose our x. -2, 1, 0, 1, and 2. Next, let's plug these in. So plug -2 in to the exponent, and it becomes 3 to the -2 power, which is 1/9. 3 to the -1 power is 1/3. Anything to the 0 power is 1, 3, and 9. When we graph these, here, 3, and 9. Graphing them, my graph looks like that. So now let's switch to the function now with an extra -1/3 in the front. All we have to do now is multiply this column by 1/3, which turns into -127, -1/9, -1/3, -1, and -3. So now notice what happens. As we graph these numbers, we start at -2 and -127, 1/9, 1/3, 1, -1, and -3. So here's my graph of the next function. Okay. Notice that they are a reflection of each other. with the asymptote still being the x-axis. Also, the blue one, this one, is a little more compressed. It's a little more pushed towards the x-axis because this is only one space away, whereas this is 3 spaces away. Right? So the blue function a little more pushed towards the axis, which is what happens here. Right? That is a compression.
I'm sorry, what's the asymptote again?
Okay, the asymptote is the line that each graph goes towards but never crosses. So in this case, the asymptote is right here. It goes toward the line, it can never cross it. Because the bottom here will keep getting bigger and bigger and bigger, but this number will never get positive. So it can never cross that axis. Alright, next. All we're going to do here is decide what these functions do. Here, I have x minus 4 in the exponent. This is going to move to the right 4. Down here, a plus moves us left 2. Here, the 10 makes us go up 10. And then this 20 right here is going to stretch by a factor of 20. And the last one, the 5 moves up 5. This 5 here is going to stretch by a factor of 5. Both of these are smaller than 1, so those are going to be decay. Both of these two are bigger than 1, so it's going to be exponential growth. Now, okay, so up to now we've worked with bases for our exponential functions that have all been rational. However, some exponential functions can have irrational bases. Okay? The most important one that we're going to talk about is this one, base e. The graph of y equals 1 plus 1 over x dx power has an asymptote at y equals e, or about 2.71828. Just like pi is about 3.14, right? Pi and e are similar numbers. We can use approximation for it and use it in our calculations. What kind of calculations are we going to do with this? Right, having to do with natural base exponential functions. Functions with base e. They are useful describing in something with continuous growth or decay. The most useful function we can use for is the continuously compounded interest function. Last lesson, 7-1, we did annual interest, which was this function. That's a t. A of t equals principal times 1 plus the rate to the t power. Okay? That function is used for interest that's calculated annually. This function is used for interest that's compounded continuously. Very big difference. This one, annual interest. This one, continuous interest. And notice that inside the continuous interest function is the letter e. So let's see how this function can work. So here's our word problem. You want a contest. At the start of 5th grade, deposited $3,000 in your account, 5% interest, compounded continuously. That's the important word. If you see compounded annually, then you have to use the other function, the old one from 7-1. If you see compounded continuously, this is a function of e. So let's plug it in. So a is going to equal 3,000 e to the 5%, 0.05 times 4 years. Okay. Working this out on your calculator will give you $3,664 and something cents. I don't remember. I think 20 cents. Anytime you see a function with interest compounded continuously, use this formula. And that's it for 7-2.